Okay, morning everybody. Happy Halloween. Uh, Today's Halloween, so we're all going to be, in theme. For those of you who want it, there are some masks and plastic masks. These guys, the party masks. A sword in case you want to hold it. Some wigs, hat, and a headband, and a couple of pair of horns. So, unless you want to be a unicorn, in which case you can just wear one horn. Okay. But just come by, get there. No one? Your kids need some spirit, man. Here are the rules. After the class, you come down here and everybody gets photographed. Why not? Okay, wear the wig. There's a wig. Look at that. All right, I'll wear the wig.
Wearing that, I think it will follow.
I do this every year. So.
I'll figure it out.
All right, let's begin. If there are any latecomers, they can always wear one of these. This is easy. This is not actually going to, get anywhere. All right. Okay, we're going to continue our series on recurrent neural networks. We're going to be looking at sequence-to-sequence models. But first, a quick recap. The story so far: recurrent neural networks are useful for modeling time series data. They can model temporal dependencies, both unidirectionally and bidirectionally. Vanilla recurrent neural networks we saw are poor at memorization because if you just use a standard recurrent neural network, the memory behavior depends more on the parameters than what is being remembered, which is not what you want. So, guys, if you want some masks and such like, they're up here. Hats, masks, wigs. There's Chantal, she's going to wear something. All right. And then they also suffer from vanishing and exploding gradient problems, which means that you can't really learn, you can't really have information being filtered back through time for them because the gradients disappear. And gated recurrent networks such as LSTMs and GRUs fix this by making memory directly dependent on the input rather than on any parameters through the use of the so-called constant error carousel. We've also looked at applications. Specifically, we looked at sequence-to-sequence models because one of the most important uses for recurrent networks is sequence-to-sequence modeling. So here you have a sequence of inputs coming in and a sequence of outputs going out. We specifically considered order corresponding time asynchronous models where outputs are intermittent. And so here, for these models, we use the CTC framework where we try to estimate alignment for training, we try to estimate the alignment of the output tokens to the input. And during decoding, we use a beam search to estimate the optimal order corresponding time asynchronous decode. So all of this you must be familiar with. And now there's a different kind of problem that we're going to be looking at today, where the input and output may not have any correspondence at all. But before that, we're going to have a brief detour into language modeling. Can anybody take a look at this code and take a guess as to which open source project this code came from? Anyone? Aha, we also have Halloween candy, guys, so you can come by and have some candy. So, Bishop, can you tell me where this came from? No idea, right? What about this? Does this text look reasonable to you, something plausible? It looks like a Wikipedia page, right? And here's actually here's, so, and even more text, something that's been, this looks like an article, like a paper with complete with proofs. Here's a Wikipedia page, or what seems to be a Wikipedia page. Now, all of these were generated blindly by recurrent neural networks of the kind that you have learned so far. In fact, the specific code used to generate this can be found on Andre Karpathy's GitHub page. And the reason I'm giving you these examples is that the models which generated these are ridiculously simple. You can download the code. The one that generated this one was trained on was LSTMs, and it was trained on all of Linux source code, and then it was just used to generate new data. And when you generate it, what comes out looks exactly like a program, right? It's perfect. It's got, I think he might have edited it a little so it compiles, but it knows everything. It opens a parenthesis, it knows to close it. It opens a curly brace, it knows to close it. Everything is completely consistent. And this code probably does nothing useful. And the machine which generated it has no idea of what is going on over here. But superficially, this is a perfect piece of code, and it has been generated blindly by a recurrent neural network. So also the same piece of code from Karpathy's page, when trained on papers, generates these very mathematical looking text with lemmas and proofs. It knows that lemmas follow proofs. It knows that there are figures, pretty much everything. It looks very consistent and coherent, and this has been done blindly and stupidly by a recurrent neural network. So this text over here, again, the same code generated, trained on Wikipedia text, generates what looks like perfectly plausible Wikipedia text. So the title for this work that was given to it by Karpathy was The Unreasonable Effectiveness of Recurrent Neural Networks. It's amazing that they're actually able to learn so much about the data that they're able to generate completely plausible looking new data. And in fact, modern text generation is a lot more sophisticated than this one, right? If you look at some of the most recent open source models, they generate things like this. In fact, this particular text is already 3 years old, but just look at it. One of the many sages of the time, the Bodhisattva Sakyamuni, was a popular religious figure in India and around the world. This Bodhisattva Buddha was said to have passed his life peacefully and joyfully without passion and anger. And it's given his age, the years of his existence, 1575 to 1611. For over 20 years, he lived as a layman and dedicated himself towards the welfare, prosperity, and welfare of others. Among the many spiritual and philosophical teachings he wrote, 3 are most important. The first, titled The Three Treatises of Avalokiteshvara. The second, The Teachings of the 10 Questions. And the third, The Eightfold Path of Discipline. So it sounds perfect. This is completely plausible. If I gave this text to you, you would believe that it was authentic. It was just blindly generated by a neural network. So how do these things work so beautifully, right? To see that, we're going to look at language models first today. Modeling language using recurrent neural networks, or more generally, we're going to look at the problem of modeling language using embeddings. So here's a standard problem in modeling language. I'm assuming, some of you are American, most of you are familiar with, the themes of the times. If you were given this text, 7 years, what is the next word? Obviously, right? You didn't have to be prompted. If I gave you ABRAHAMLINCOL, what is the next character? N. So that's the problem of language modeling. I give you a sequence of text, a sequence of symbols, and you have to guess the next one. And obviously, you're doing a fantastic job. So how do we do this? How would you build a model to do this? The first thing, of course, is, neural networks don't deal with symbols, with text. You've got to convert it to some mathematical formalism. And so we're going to represent words or characters as one-hot vectors, which means you'd pre-specify a vocabulary, a dictionary, saying here are all the words in my dictionary. There are 100,000 words that you're considering, words ordered 1 through 100,000. And now each word is going to be represented as a one-hot vector in the standard format, a vector of zeros with a 1 in the position that corresponds to the word. And so also, if you were working off characters, like in the second problem, now you'd have one-hot embeddings of characters. For a word-based model, you might require anything between 100,000 and 1,000,000 words. For a character-based model, you could get away with about 100. So now, when you want to predict the next word in the sequence, like we saw in the examples just now, what you would be given is the first n-1 words, and you have to predict the nth word. So the nth word is some function of the first n-1 words. The problem of language modeling is learning this function. Now, how would we do this? You're going to obviously represent each of these words as one-hot vectors. All of these one-hot vectors going into your function. That function is going to be generating a probability distribution, or more ideally, a one-hot vector representing the next word. The issue here is dimensionality. Now consider I'm trying to do something for English. Then you need about 100,000 words. So that one-hot vector is going to be 100,000 dimensions. Now if you're doing something for Russian, you need 400,000 words. So that one-hot vector is going to be 400,000 dimensions. And if you're doing something for more complex languages, those dimensions are going to be even greater. But then, first, why do we need one-hot vectors? Why am I using one-hot vectors? Why can't I use any other kind of vector representation which uses fewer dimensions? Does anybody want to take a guess? There's some.
Is this a way to make something distinct over a set of numbers?
Yeah, but I could always be using some binary coding, right? Yes.
Because the word lengths keep varying, so
Well, no, but the word, there's no length to the word if it's a one-hot vector, right? So if I gave you any other vector representation other than one-hot vectors, then there's a notion of a distance between two vectors, right? So if I gave you two vectors, a vector representation for each of two vectors, then you can compute the distance between these vectors. And if you assign vectors to words, then you are implicitly assigning some kind of a distance between words. You're saying these words are closer together and these words are farther together. In the absence of any information that justifies this, how do you decide what these distances must be? Doesn't make sense. You don't want to be assigning some kind of distance to between words, right? So what is the advantage of one-hot vectors? What is the distance between any two one-hot vectors?
Equidistant.
Pardon me?
Equidistant.
Yes, but what is the distance? Square root of 2, right? So any two vectors which are not identical will be square root of 2 apart. So basically, the one-hot representation makes no guesses about which word is closer to which word. And so you want to have this agnosticity. You just want to say, you're going to be agnostic to the words themselves and not try to force some meaning onto them. And that's why you use one-hot vectors. But then here is the problem, right? One-hot vectors are a very, very wasteful representation of data. If I have 100,000 words, I'm working in a 100,000 dimensional space. In this 100,000 dimensional space, how many points do I have? Using one-hot vectors. Pardon me? 100,000, right? So I have a 100,000 dimensional space, and in this I'm using only 100,000 points. And here's the worst part of it, right? If I have a one-hot vector which is of this kind, 0, 1, 0, 0, 0, this represents some word, right? But what about this one? Does this represent anything? Just wiggling the numbers off by teeny, teeny, teeny epsilon gives you something completely meaningless, right? So you have all of these points. You're using exactly 0 volume of the space. because every point is just an isolated point. But moreover, if you look at the density of points per unit volume, it's abysmal. So here, for example, in if I were to place all of the one-hot vectors on the corners of a cube of side R, then the density is going to be, there are only n points in the space, right? But the cube volume is R raised to n. So this is the density. This is pathetic. It's going to be of the order of 10 raised to minus 100,000, 10 raised to minus 5 for 100,000 dimensional, 100,000 vocabulary language. So now this is not a very useful thing to do. So the reason we use one-hot representations is that they make no assumption about the relative importance of words. All word vectors are the same length, and the distances between words are all the same, right? So we like this idea, but then we don't want to work in this extremely high cursed dimensionality. You would like to reduce the dimensionality. And ideally, you would also like to get some, but then if you reduce the dimensionality, you're going to lose this equidistance property between words. So that means you want to reduce the dimensionality in a way where the distance between words also makes sense. So basically, we want to project the points into some lower dimensional subspace, which is to say you're going to start off with your, instead of using the one-hot representation W, you could just arithmetically, you'd be using some projection matrix P, and now the new representation is going to be P times W. And that new dimensional, the new representation is going to be in the same, is going to have the same dimensionality as the column dimension of the number of rows of P, which can be much smaller. It can be orders of magnitude smaller. So you want a linear transform, which projects all of these data onto some subspace of the subspace. And when you do so, firstly, you're sort of reducing the dimensionalities. And one benefit of this is that now, if you've gone from the n-dimensional space to an m-dimensional space, your density has gone up from 1 over r raised to n to 1 over r raised to m, which is a much more efficient and effective use of the space. And also, if you properly learn this projection, then the distances between the projected points could be meaningful. They could actually make sense, and the positioning of the vectors on this plane will tell you something about how the words relate to one another. So the objective is to actually learn a projection which gives you a lower dimensional representation that's also meaningful. Now, let's go back and look at how we can do this. If I'm projecting all of my words down, now this means that my prediction function in language modeling is going to be using P times W rather than W, right? Every single word is being projected down by pre-multiplying it by the matrix P. Now, multiplying a vector by a matrix is like having a single linear layer in your network, correct? So that's the same as having, you'd be putting every one of these one-hot vectors through this projection P before passing them into a prediction function. But then those, basically multiplying by matrix P is like putting it through a network which starts off with, which converts n components to m components. And once again, because every one of these words is being projected down by the same matrix, that means every one of these guys is the same linear layer, right? And so this whole thing, if my F is also a linear neural network, this whole thing is a shared parameter network where where the inputs are all being transformed by a linear layer whose parameters are the same for every one of the inputs, right? Now, assuming I'm doing this, let's look at the simplest model. I can say that I'm going to predict each word based on the previous n words. So 7 years. I didn't have to tell you more, you knew the next word was a go. So 7 years. If you just by looking at the previous 5 words, you're able to predict the next word, the 6th word. So if I want to mathematicalize this, it means that my prediction is going to look at the prediction of the 6th word, W6, is going to look at W5, 4, 3, 2, and 1, right? or in this particular example, each word is being predicted based on the previous 4 words. And so this is what your prediction is going to look like. I'm going to be, my language model, if I were to be thinking of it as a prediction network, it would be looking at the first word, 4 words, and be predicting the 5th word. Then it would look at words 2 through 5 and predict the 6th, 3 to 6 and predict the 7th, and so on. This is going to be my language model, right? Except that the predictor itself is now going to take the projected down version of the words, because we want to project them down from the high dimensions to low dimensions. Now, there are a couple of different ways of doing it. The one of course, is simply to say that I'm going to use the previous. So let's look at the first problem. What is this matrix P? What is this magical projection P, which brings the words down to some meaningful dimensionality where relationships make sense? So there are several ways of actually doing it. The simplest one is this guy here, where you try to predict every word based on the previous n words. You can have various alternatives. Since the objective here is to learn the projection P, you can say I'm going to predict each word based on the previous k words and the subsequent k words, because obviously the future tells me about this word as much as the past does. Or the alternate, which is called the skipgram model, where you use each word to predict each of the previous 3 words and each of the previous succeeding 3 words. And then you can have other formalisms. Now, the idea here is that at each time, this model is going to be making a prediction. But what does a model actually predict? It's not going to be predicting a word, right? What would the output be? What is a prediction? It's actually outputting a probability distribution over words, is it not? And so when you're outputting a probability distribution over words, the way you would train it is that you're going to have a probability distribution over words at each time. And then you actually have the target word at each time. You would be computing the KL divergence between the target word and the output probability distribution. And the divergence of that, the derivative of that, is what is going to be back propagated to update all the parameters of the network, right? And so same thing over here. You'd be outputting up here, you would be outputting the probability distribution for W4. You have the actual W4. The error is going to be back propagated to update the parameters. Then you take a step forward, predict W5 based on all of the neighbors, back propagate the error, and so on. In the second case, using W7, you'd be predicting those 6 words, 3 on either side, which means that you'd be outputting 6 different probability distributions. You'd be comparing those to the actual words for each of the 6 words. And then the sum of all of these divergences is what is going to be used to update the parameters of the network. But then you take a step forward, and for the next word, you use that word to predict everything on either side and repeat the process. Clear to everybody? Right, okay. So how well does this work? The examples that I'm going to show you are basically from this model. So what it should be in SIBO. What is that? Okay, so if you look at this, how well does that work? You start off from the high dimensional one hot vectors, and these are projected down in this example. I think they projected it down to 1,000 dimensions, and then this is a 2-dimensional principal component analysis and representation. And here's how the various words in the language are positioned in this 2-dimensional space. And you find this very interesting. Don't quite represent the color that indicates shared parameters. I'm not sure what we're speaking of over here. Where is the color? Okay. So anyway, so look at this. I have this China and Beijing. These have been positioned in this space. I have Russia and Moscow. They have also been positioned in the space. If you look at the vector that connects China to Beijing, it looks exactly like the vector that connects Russia to Moscow, or Japan to Tokyo, or Turkey to Ankara. So country minus capital seems to be more or less the same or very similar for all of the countries over here. In other words, we've learned the projection has successfully learned the relationship of capital. It was not given any external information. This is just from analysis of language. Or here is, okay. Before that, there was actually other examples. I should have shown this, where they show that man minus woman equals king minus queen. So it learns the notion of gender and several other such beautiful relationships through this very simple mechanism. Anyway, here's your first poem. Yes.
When we were trying to learn the probabilities of the words, how would the ground truth be produced?
So here is the thing, right? This, yes, we'll look at that. But if I would be given a sentence, 7 years ago, right? So I use 4 years ago, and then I predict and, right? But I already know it's and.
Yeah.
So the ground truth is part of the language, right?
Yeah.
All the trains.
So we are forcing it to learn one hot, but we don't want it to learn one hot.
No, we're trying to teach it to learn. What we are really doing is this. You're trying to predict this word, say 4 score and then 7 years ago, right? And then you'd be using these guys to predict the word 7. It's going to give you a probability distribution over words. You'd be comparing that to the one hot representation for 7. There's a divergence. And then you'd be using that to update the parameters of P, the model and P, right? And that's how you learn P.
Okay. Then
Right?
P is what we use for the.
P is what you're going to use for the projection. Let me stop here. We've gone way beyond the minute. So anybody on Zoom want to take this question?
2, 3.
2 and 3, right? Okay. 1, 2, and 3, right? The distance between any two non-identical one hot vectors is the same. We know that this is why we use one hot representations, right? Words are represented as one hot embeddings because they do not impose any a priori assumption about which words are closer than others. Word embeddings derived from language models are lower dimensional real valued representations where the distance between words can be a meaningful representation of their closeness or relationship. So everyone get this so far? And did we also get how we learned the P? So again, going back, the way you learn the P is you use one of these various models, and I just have to give you proper sentences. I give you sentences in English. When I give you sentences in English, you always know what the next word is, or you know what the current word is. So I give you a sentence. I give you a reading of, The Tale of Two Cities. Starting from the beginning to the end, if I give you the first 4 words, you're going to predict the 5th word, but you already know what the 5th word is. So the divergence between those two, the probability distribution, computed after seeing the first 5 words, and the one hot representation of the 5th word, that is going to be back propagated to learn both the parameters of the network over here and this projection P. So you can use the entire text. There's no additional training data. I just give you text, and that's enough to learn this model. Same thing over here, right? For each of these models, if I give you text, then in the first case, at any point for any word, I know what the previous and subsequent words are. I can use those to make a prediction, compute the one hot, compare it to the one hot representation of the word that I know is there, and then use those to compute the derivatives, which are then used to learn these projections, right? Okay, so continuing on. What are these, if I were to use recurrent neural networks now for modeling language, how do I do that? The recurrent neural network now is not going to say what we saw so far were time-delayed neural networks, right? Where you just saw the past 4 words and you predicted the 5th word. Or you saw the past few words and the next few words. So these were finite response networks. But more generally in language, if you want to predict a word, you want to look at everything in the history. For that, you would use a proper recurrent neural network. And in that case, this is what the network is going to look like. Everyone with me? You still have this issue of projecting things down to a lower dimension because you don't want to be working off one-hot representations directly. And then you're going to have lots of text. And so again, I'd be reading The Tale of Two Cities, and that could perhaps be my training text to learn a language model for Charles Dickens. I know all the words in the language. At the first word, I'm going to be trying to predict the second word. I'll actually be outputting a probability distribution. I compare it to the second word. Then after seeing the first and second words, I'd be trying to predict the third word, which I already know, right? And so I can just go through the text and keep trying to predict the next word. And then the prediction error is what is going to be used to actually update my network parameters. The network itself can be an LSTM of any number of layers. So you don't need any explicit labels, just a sequence of text will do. Now, how did we do this business of generating text earlier, the one that we saw, where I showed you some code had been generated or some Wikipedia page had been generated? Here's what I do. I would seed, once I've trained my language model, I can seed it. I give it the first 3 words, let's say, right? If I give it the first 3 words, you have some basic computation. You don't need to do anything with these outputs, but at the third word, it's going to be outputting a probability distribution. From this probability distribution, I can draw the next word using some process, right? Whatever the drawing mechanism might be. And that's going to give me W4. Now the W4 is now going to be fed back in as the next word. And now it's going to be generating a probability distribution for the 5th word, from which I'm going to draw the 5th word. And that W5 is going to be fed back in as the next word, and then you get a new probability distribution from which you generate the next word, and so on. And you'd keep doing this until some natural termination occurs. Now, what is a natural termination? If I'm generating code, what would be a natural termination?
Balance.
The function is closed, the brackets are balanced, so you know when the thing is complete, right? Or here is an example where I don't need to worry about generation at all if I can play this and if it will be heard. So this is, someone just trained a recurrent neural network on MIDIs, and this is automatically generated, right? I don't have to worry about termination, and it sounds quite fairly decent. And now, again, this is a very trivial model. Works surprisingly well, right? But more generally, when I'm working with text, when do I stop? When do I know I am done? So in order to know when I'm done, I'm going to have to indicate it. A sequence of words by itself does not indicate if it's a complete sentence or not, right? 4 score and 8. Is this a full sentence? You don't know. It could be, right? Maybe somebody just wrote 4 score and 8 and went home. So you need some way of indicating whether it's a complete sentence or not. So to make it explicit, we're going to add, I don't know if it's the complete sentence, I don't know if it's the initial portion of a sentence, I don't know if it's the final portion of a sentence. There is no indication over here. I need explicit indicators. And so the explicit indicators are going to be these 2 symbols, the start of sequence symbol and the end of sequence symbol, which can both be the same in some cases. And so I'm going to, anytime a sentence begins, I'm going to precede it by start of sequence. I'm saying, here's the start of sequence and the sentence began. And then so here's end. When a sentence ends, it's going to be terminated by an end of sentence sequence. So over here, for instance, 4 score and 8, this is the middle of a sentence. It has no indicator of start of sequence or end of sequence. On the other hand, SOS, 4 score and 8, it means that these are the first 4 words in the sentence because it began with the start of sequence marker. Similarly, 4 score and 8 EOS means that these are the last 4 words in the sentence because then after that you had the end of sequence marker. If I have SOS, 4 score and 8 EOS, then it's a complete sentence because the sentence began, you produced 4 words, and then the sentence ended, right? So you don't actually need two separate symbols for start and end of sentence. You can just have one, but the point is implicitly there are two. You have to indicate the beginning and ends of sentences. And so over here, when I'm generating language, I'm going to add one more term to my vocabulary, which is the end of sentence marker. In fact, I'm going to implicitly add two terms, the start of sentence marker and the end of sentence marker. And then the start of sentence marker is never going to be generated. You're never going to start, right? The probability that the first symbol is SOS is 1, so you don't need to explicitly think about it. You need to know when the sentence ended. And so over here, after giving the first few words, you're going to keep generating things till an end of sentence or end of sequence marker has been generated, at which point you stop. So here's another point. This is an easy one, so I only give you 5 seconds. Okay, I'll give you 5 more. Okay, does anybody want to tell me which are the complete sentences here? Is the first one a complete sentence? Second one? Third? Third is yes? It doesn't have a start of sequence marker, so it is not. A complete sentence begins, has a word sequence, and ends. This is an end, right? And the fourth one, it's not. Because if the beginnings and ends are not marked, then they are not present. That answer your question, right? Any questions on Zoom? Okay, perfect. All right. Yeah.
What do you think this imbalance of classes? Do we need to handle that, or do we ignore that because?
What do you mean imbalance of classes?
Lots of SOS and US.
Yeah, you need to know when to terminate. It's not an imbalance of class. The end of sentence is the most frequent symbol, period, right? So,
don't need to.
Yeah. So, all right. So that was all about modeling language and how to use lower dimensional representations to represent words. But then let's return to our problem, that of generating sequences. And the problem of sequence to sequence modeling was that of creating a model which can take in a sequence of inputs and produce an output sequence where the input and output sequences may not even be the same length. So there are two specific cases. The first one is where there's an order correspondence between the input and the output. So the output is a sequence of symbols, and the first output symbol corresponds to the initial portion of the input. The second output sequence symbol corresponds to the second portion of the input, and so on. So there's a order correspondence. And this we've already seen. This is what we discussed in the last week. The second one is the more interesting problem, really, where there's no guarantee of any kind of correspondence between the output and the inputs. For example, machine translation. I ate an apple, ich habe einen Apfel gegessen. That's a single word in the input could correspond to multiple words in the output. The order might change. Or you might even have something like this in a dialogue, in a system that's generating dialogue responses. The input could be my screen is blank, and the output must be please check if your computer is plugged in. There's no apparent relationship between the input and the output, yet this relationship must be learned, right? And it might surprise you that neural networks do exactly this job. This very complicated, very semantically meaningful response is done by a dumb system which knows nothing other than the data that it saw. Anyway, how does one model this kind of thing? We're going to use this network. This is what we'll call a delayed sequence to sequence. It sees the entire input, and then after having analyzed the entire input, it generates the entire output. And so over here, here's what happens. You're going to analyze the entire input, and then out here, this node, this hidden node captures all the information about the input. And then so this is what that process might look like. It's a recurrent network where you're going through all of the inputs, and at each time, the recurrent network is taking in the hidden state at the previous time and the current input. And when finally you have got an end of sentence marker at the input, that's when you're done. You can go to the next phase. And so the hidden state, the final hidden state, this guy over here, is the hidden state of the network when the input is an end of sentence marker. Then subsequently, the second portion of the network kicks in. It takes this guy as input and produces the rest of the outputs. So this is going to look something like this. The upper portion of the network is the one that generated the hidden state for the input. The lower portion of the network is now just going to start off. There'd be some initial H0 because it's a recurrent network, right? So then that H0 in the simplest form is simply going to be the hidden representation forwarded to it by the portion of the network that processed the input. And then I can just go through this recurrent. There are no further inputs. Observe that there are no further inputs over here, right? And then I can just sort of recurrently process the hidden states. And then at each time from the hidden state, I'm going to compute an output probability distribution. And of course, the next value for the hidden state. And from the output probability distribution, I can draw a word or a symbol. And that's going to give me my output sequence, right? So again, remember that at each time, what the network outputs is a probability distribution from which a symbol or a word is drawn. Now, what is a network? What is the problem with something of this kind? Can anybody identify a problem with this? Yes, yes.
It's biased very heavily towards information from the very last word that was.
That's one of the problems. That's a good one. But we'll address that in the next slide. There's something even more immediate.
How do you know the length of how many outputs it takes?
You're going to stop when you get an EOS. So here's the thing. What is output at any time has no bearing at what is output at the next time, because the network is generating a probability distribution and the drawing is an external process. So right here, for example, if I, at this point, from this, there was a distribution computed and I randomly sampled it. And I chose the word "an." Then if I were to follow the rules of English, the next word must begin with a vowel, right? There's nothing here which tells me that the next word has got, that words that start with vowels must be more probable at the next time. That's because whatever is being chosen at this time is not being referred to at the next time. Every word is being treated independently. So you're likely to get complete gobbledygook because you're just getting probability distributions and you can choose random words from it, and the word chosen at any time is not being used again in deciding what the next word must be. So what would the cure for this be? Anyone? Thank you, right? I can just pass that, I can choose the sample value and push it back in. And so here is what I would do. So if I were to translate English to French or German, right? I'm going to have the initial portion of the network, which analyzes the input and produces the final hidden representation. And the hidden activation at the EOS stores all the information about the sentence. James, your point is very valid, and it's important enough that we're going to devote a class on it. But once that is done, the second recurrent network, so the first recurrent network actually analyzes the input, generates this hidden representation, and then the second recurrent network uses the hidden activation over here as its initial state and start of symbol as a initial input and begins to generate outputs, right? So, and the output production continues until the end of sentence marker is generated. So here's what you would do. You're going to use this red state, and then at the next time, the input is the start of sequence because you're generating something from scratch, which means that you have to indicate to the network that you're starting. And then you would get A, and then at that time you'd draw some output. And now that is going to be used as the input of the next time to the recurrent network. And now you're going to draw the next word as the output, and so on. And you keep doing this until you get all the way to the end. Now observe over here is that, if you observe over here that the specific output being generated depends on the specific outputs previously generated. So if I had not generated the word ish at the first instant, if I had generated something else, right, that word would have gone in and it would have changed the future forever. So this has the effect of having the future sort of being dependent on the previous outputs. Now, what does the second portion of this network look like? You've just seen this, right? What is it? Guys, thank you. Can you say that aloud? This is a language generation network, is it not? This is basically all we did. So now what we are saying is that you're passing the input in, you're generating a hidden representation. That hidden representation is now being passed to a language generation network, which is only being seeded by the startup sentence symbol. And that is going to move ahead and produce the rest of the sentence, right? And this network itself in the middle can be arbitrarily complex. It can be a single layer of LSTM. There can be multiple layers of LSTMs. It doesn't really matter. I'm going to keep using the one layer network as my one hidden layer network as for my illustrations, but that's just only for illustrative purposes. So here's what the pseudocode is actually going to look like. The inputs are going to be processed by the initial portion of the network till you get the final hidden state out here, right? This guy. And then after that, that hidden state is going to be passed in as the initial hidden state. The initial output symbol is the start of sentence. So to the recurrent network, at each time you're passing the current hidden state, which would initially be just this guy, and the latest output symbol, which is initially just going to be the start of sentence marker. It will process those and return to you two things: the updated hidden state and the probability distribution for the words at that time, right? Output words at that time. And then from this probability distribution, you're going to select the next word. And then you go back to the next instant. And at the next instant, the new hidden state and the word that you have just chosen are going to go in, and it's going to give you, once again, it's going to give you the next updated hidden state value and the probability distribution for the next word in the sequence from which you draw a word, and you'd keep doing this. When would you stop? You would stop until the output was the end of sequence marker. Everyone with me so far? Right? Any questions? No. Okay. So observe over here that if I drew a different word at time t, that differently drawn word is going to go back into the recurrent state, and so it's going to change the output forever. Right? All right. The portion of the network that processes the input is going to be called an encoder. It's encoding the input, and in this specific case instance, it's encoding the input, it's processing the entire input and generating a representation which is being shown by the hidden state of the red box. The portion of the network that generates the output from this guy is what we will call the decoder, which takes this hidden state and processes and generates the output. This is just in this particular example, this is just a language generation network which took the hidden state generated by the encoder. Yes, Eric?
Are those the same weights for the green and blue? Or are
They're different. The encoders and decoders are now completely different networks, right? And in fact, the hidden state representations may be different sizes, in which case whatever came out from the red box would have to be transformed through some linear layer to the correct size for the green portion, or for the decoder portion, okay? So in more detail, you're not actually going to be passing words in. You're going to be passing, because words are one-hot representations, you're going to be passing a projected down version of the word. So you're going to be passing, and so these projected down versions of the words are what we call word embeddings. I forgot to introduce this terminology earlier. So you'd actually be passing in the embeddings of the words that you've generated so far. On the output side too, you're going to be passing in embeddings of the words that have been generated. Now observe over here, if I were translating from English to German, the input has a vocabulary that comprises English words. The output has a vocabulary that comprises German words. So the input and output vocabularies can be very different. The input and output embeddings, the transformations that convert the one-hot representations to lower dimensional vectors, can also be different. And so over here, this works on a completely different vocabulary than this guy. And so correspondingly, the embeddings that you will get for these words are going to be very different from the embeddings for these words, right? I mean, you could always have a situation like a dialogue system where the input and output are the same language, in which case the piece would be the same throughout. But if you're doing something like translating from English to German, then on the input, on the encoder side, the projections are going to be through some matrix P1. On the decoder side, the projections are going to be through some other matrix P2. Right? Okay. Questions?
These two are completely different networks.
They're completely different networks. They communicate through the hidden state. Yeah.
If the task is language generation, then it makes sense to draw the symbols from probability distribution. But if it's translation, shouldn't we be picking the max logics or something like that?
So the process of drawing, let's take a look at that. Thank you. Right? So what is the network actually producing? At each time, it's outputting a probability distribution. And from that probability distribution, you're drawing a word, correct? So at each time, what is this probability distribution? So if you look at time 0 at the output, this is the probability distribution over the words, the probability that of each word in the vocabulary, given, and what has been given everything that has gone into the network. So at each time, by the way, I'm not explicitly showing the embedding matrices over here, just to simplify illustration. So, but at each time, you're computing the probability for every word in the vocabulary, given the entire input and the, given all inputs to the network until that time, right? So over here, it's basically, if I'm looking at the kth word, what are all the inputs that have gone in? It's got the entire input, x1 through xn, or x0 through xn minus 1, depending on how you index it. And then in order to generate the kth word, it has also seen O0 through OK minus 1, right? So at each time, the network is actually outputting a probability distribution over the words given the entire input and all the previous words that have been generated, because they have been fed back to the network, correct? And so the word is actually drawn from this distribution, and this drawn word is what is being fed to the next time. And now that drawn word has gone back into the conditionals over here. And now we're going to get a new probability distribution that includes that word as a conditional. And then you're going to draw the next word from that one, and so on. So you're continuing this process, but at each time, remember that the probability distribution that the network is computing is the probability over all words in the vocabulary, given the entire input, and all the words until that time, all the output words until that time, right? This making sense? Right. So, and this process is going to continue until the end of sequence marker is drawn. Now, what exactly happens over here? So this is basically, so that's what we had over here, draw word from YT. And we were drawing some word from the distribution. Now, Lakshya thinks that we want to just pick the most likely word in a translation example. But let's go back and look at what's happening over here. What is the network's purpose? The network is translating one sequence to another, correct? So it's taking an input sequence, it's generating an output sequence. As a probabilistic machine, the network wants to determine the word sequence that is most likely given the input word sequence, right? It wants to compute, it wants to determine O1 through OL that has the highest probability, the sequence O1 through OL that has the highest probability given the entire input. That is the problem of sequence to sequence conversion. Now let me break this down. I can say P of O1 through OL given inputs I1 through IN is Bayes rule, O1 given the entire input, P of O1 given the entire input, times P of O2 given O1 and the entire input, times P of O3 given O1, O2 and the entire input, and so on, right? And what is this guy over here? P of O1, this term is simply the probability assigned to symbol O1 at time 1 by the network. The second term is the probability assigned to the symbol O2 at time 2 by the network, and so on, right? So basically, we want the probability of any word sequence, assuming that the same words that output words have been fed back into the network. This assumption is critical, right? Then the probability of any word sequence is the product of the probabilities assigned to the individual words in the sequence by the network. Everyone with me, right? And so what we really want to do is to find the O1 through OL such that this probability is highest. The product of the probabilities assigned to the various words in the sequence is highest. Everyone with me? Right, okay. So given this, and given also that the word that I have chosen is going back into the network, how do I choose the word at each time such that this product probability has the highest, this product has the highest, is the maximum, this product probability is the highest. Lakshya's choice was, let's be greedy, right? Now will greedy work? What is the greedy example over here? Here I'm going to have, at each time, the network generates a probability distribution. The greedy solution is to say I'm just going to pick the most probable word and feed it back to the network, right? But then that's a problem. You cannot just pick the most likely symbol at each time, because this may cause the distribution to be more confused at the next time. So, and choosing a different, less likely word at this time could cause the distribution of the next time to be more peaky, resulting in a more likely sequence overall. Yes?
Is there a dynamic programming solution?
Yes, there is, right? So, okay, that was quick. Let me get to it, right? So to give you an idea, right? Let's say I'm generating some word sequence, and I'm given some, let's say I was performing speech recognition rather than machine translation. So I've heard some audio. Then at some time, you're given this choice, the second word, the first word you've chosen to be he for whatever reason, right? At the next time, you find that the word nose, which is the object on my face, has a probability of 0.5, and the word nose, which is a nose with a K in front of it, has a probability of 0.49, right? If I were to use the greedy approach, I would choose nose, the one on my face, right? But when you say he knows, is that a meaningful sentence, right? It is not. So then when you use he knows as the input and ask the network, what is the next word? It's going to be very confused. It's going to give you more or less, a random set of low probabilities to all the words in the language. So when you pick the next word, whatever the probability is, and multiply that word's probability to the probability of the first two words, the net is going to be small, right? Now, on the other hand, although knows was 0.49, it had a lower probability than knows. But if I had chosen that, he knows is a very nicely structured sequence of words. So in that case, you're going to find that some words just end up with high probabilities, where the rest simply become unlikely because there's no confusion. There's lower confusion. And so now if I pick the highest probability word from this set and then multiply its probability to the probability of he knows, the combined probability of the sequence of three words is going to be higher than if I had chosen knows in the second case, right? So which is why this greedy approach is not going to work. Because what happens now is going to be influencing things into the future, and choosing something wrong now can kill you way down the line. And it's not even that simple, right? Because when I'm choosing a word now, I don't know when it's going to be influencing things. For example, let's say at the very first word, my choices were thee and he because they both sound similar. I just chose he because it was 0.5 as opposed to 0.49 for thee, right? But if I had chosen thee, the next word maybe still nose versus knows, but the nose is a much more structured thing, and I could end up, based on what happens afterwards, it could end up with a higher probability overall. So to know that the correct thing to have picked was the word thee and not he, I would have had to wait 5 words out to see what happened cumulatively. But then, you're picking things on the fly, right? If you're picking things on the fly, you don't have a view into the future if you're doing things in a greedy manner. And so as a result, you find that the choice of the wrong word early may cumulatively lead to a poorer score overall over time. And so, because in general, it's impossible to know a priori which word leads to the more promising future. And so, in general, making a poor choice at any time commits us to a poor future. But the problem is we cannot know that if we are being committed to a poor future at the instant of drawing. So here's another way. We know that being greedy can be bad, right? But if I were to choose randomly, according to my probability distribution, then I had nose with a probability 0.5, nose with a probability 0.495. If I had randomly chosen, there was a reasonable probability that I'd chosen the second word, and I'm going to get a more structured sentence overall, right? So in fact, it turns out that a more reasonable procedure over here sometimes is not to choose greedily, but to actually randomly draw from the process, from the probability distribution, according to the probabilities assigned to the words by the network. And so in this case, if you looked at what happened out here, when you're looking at draw the next word from the distribution, you'll literally be just randomly sampling a word from this distribution. And that's what you'll be using as the output. And you keep doing this until you sample an EOS. This is, in fact, randomly choosing words at each time can give you word sequences that are more probable than just greedily choosing the most likely word at each time very often. So it's a pretty good solution. But is this guaranteed to give you the most likely output? No, because you're being random, right? So let me go to our hero here. How would you solve this problem?
I think you can solve the very last, working backwards from the EOS, and then find the most probable one backwards all the way to the beginning.
It's still, there's conditional, right? You don't know the EOS until you've seen everything in the beginning.
Yeah, I don't know how to fix that.
You do actually, right? But anyways, you have half the answer. Let's see the rest of the answer. Okay, I'm going to give you 15 seconds, guys. These are 3 very easy true-false answers, questions. Is there a problem with the quiz? False? No. Question 3 has only one option? Sure. Well, there's a bug. Okay, so it doesn't matter, right? You're attempting. So can someone on Zoom look at the slide and tell me what is... Oh gosh. Okay, for greedy decoding, we choose the word that has been assigned the highest probability at each time. True, right? In decoding through random sampling, we randomly choose the next word according to the probability assigned to it by the decoder. Also true. The procedure used for randomly sampling a word for a distribution has been presented in today's class. Where did I present it? Right. Yeah, okay. What are you going to do with it?
Normally we'd have access to a function that can
So we haven't actually discussed an algorithm to draw a word from a probability distribution. in today's class, right? I just said you can do it and you're believing me, and it might just be an impossibility. I'm assuming that you know how to do this. I have been surprised in the past where many students in class don't actually know how to draw a word from a probability distribution. You should be able to write a code for it. It's 2 lines of code. So it's true, true, and false, guys. I have not given you how to do this third thing, not in class, right? I know you know the procedure, but that's not the same as me presenting it. Now, all right, so here's the situation. The choices you make can get you stuck, right? Making a poor choice at any time commits us to a poor future. But we cannot know at that time that the choice was poor. So we've seen a solution to this in the last class when we were doing CTC decoding. How did we do that? Pardon me? Can you say that aloud? Okay, he mumbled, I couldn't hear him, so I'll give you the answer, right? I'm going to retain all my choices. So what happens is, when I give it the startup sequence marker, it's going to generate probabilities for all the words, right? I'm going to make as many copies of my network as I have words in my vocabulary. And then I'm going to feed each copy one of the words in my vocabulary. But then each copy has a probability assigned to it. And the probability assigned to it is the probability of the word that I have entered. So the probability of the word that's entering the network at that point in time, right? So now this network over here is giving me the output probability distribution over all words when the first 2 words in the sequence are SOSD, right? This network over here is giving me the probability distribution over all words when the first 2 words are startup symbol V, and so on. So I'm considering every possibility. And then at the next time, I'm going to do the same thing. I'm going to look at the sequence of words. Yes, I can see him shaking his head, but you also know the answer, right? So I can take all of the words in my vocabulary and feed those into the different copies of the network. So the hidden state is always going to keep getting propagated, right? What is changing is the inputs, but then what happens over here is that by the time I come here, all of these hidden state values are going to be different because they receive different inputs. So also all of these hidden state values are going to be different because they receive different inputs. The arrows are just telling you how the values are being propagated. Now, James, what is the problem with this?
The tree is really big.
The tree is going to blow up. What is the solution?
I actually haven't figured it out.
You did. We did this in the last class. Top K, right? I can just keep the top K guys. So prune. Every path has associated with it a probability. And the probability specifically is the probability of the word that is going in. I can just keep the top K, right? And then, so if I decide that my top K are the top 4, these are the 4 that would remain. Then I'm going to, so I have top 2 in my example. So these are the 2 that would remain, right? Then I'm going to expand all of these guys. But if I expand all of these guys, now if I have V words in my vocabulary, at this point I'm going to have 2 V entries. Of these, I'm going to retain the top 2. What is the probability? I'm going to retain the top 2 based on some probability, right? What is the probability that I would use to decide which I must choose? Yes?
The first word times the second word.
First word times the second word, right? Because this guy, this one already has a probability assigned to it. So this has a probability conditioned on this word. So the probability assigned to this word over here by this network times the probability assigned to this word over here by this network. You're going to have that for all of the entries in the network. You pick the top K, top 2 in this case, top K, kill everything else, right? So note that the selection is based on the product, right? The product of the probabilities of all the words on the input path. And keep doing this until eventually when you keep killing it until something gets an end of sentence, end of symbol marker. If it gets an end of symbols marker, there's really no point in performing any additional computation, the thing has terminated, right? But then you have to be careful. If I look at this way, this sequence of words has terminated. Does that mean that it's my most likely sequence of words? Why not? You don't. So this sequence of words might have a probability of 0.1, and this sequence of words might have a probability of 0.9, although it has not terminated. Right? So now I'm only going to be expanding this guy. And I'm going to keep expanding it till I get a sequence terminating with end of sequence that is the highest probability sequence so far. And that's what I'm going to output as my final word sequence.
Why
Yes.
is the probability high?
Pardon me?
Why is the probability high?
Which one?
You said it's 0.9.
Because you're keeping everything, right? If you're keeping the top two, you might have find that, the top one is 0.9, the top second one is 0.1, third one is, right. So, yeah.
What if the end of sequence tag never show up in top K?
You're going to keep going till it does, right? But usually what will happen is that can happen. Then you're going to have an upper bound and say, I'm not going to generate. I know that this length can't be more than 100, stop. But yeah. This is inference, right? During training, okay, we will get to training. I have 10 minutes, yes. At each time, you only have k branches.
So for each word, you need to generate the whole. Okay, that is one. Okay.
At each time, you only have k branches alive, right? So you're fine. You're going to be pruning before you extend it. Now, the nice thing over here is that I can use this process not just to generate my most likely hypothesis. I can also use it to generate my a guess for my second most likely hypothesis and my third most likely hypothesis, because I can just pick the first one, that the highest likely one that ended with an EOS, but then the rest of them can still be evaluated, and I can generate my top end hypotheses. I have some pseudocode for it over here. I'll skip that, but there's a poll. Okay, 5 seconds, guys. All right. Someone on Zoom, we want to take the first question? All right. So theoretically correct decoding requires you to evaluate the entire tree representing every possible word sequence to select the best one. This is true. Beam search is not theoretically correct. Why is it not theoretically correct? Because I'm retaining the top k and the best one might have been one of the ones that I killed. Right? This is just your best guess. All right. So this is answering Adnan's question on how do you train this thing. So consider that I'm doing this machine translation problem, right? What I would have is, now here is the crazy thing that I want you to keep track of. So normally when we train a network, the input goes in and the output comes out, and you just generate the output and compare the output to the desired output, and you compute the loss, correct? But here, we are going to do something different. If I were to just start off with a random initialization of my network for a machine translation problem, and I gave it, I ate an apple at the input. In the initial stage of the network, what's likely to come out? It can be complete garbage, right? It can be absolute garbage, regardless of the policy that you use for, mechanism that you use for drawing words. So you want ich habe einen Apfel gegessen or ich esse einen Apfel, right? An apfel. And so this is the output. You know that the output must be 4 words long, but this could generate something like 250 words long. because you have no control on the process, right? And now how do you compute the difference? And how do you train the model? It's going to be quite impossible. So now we're going to cheat. In everything that we've seen so far, when we train neural networks, we gave the network an input, and the output generation was just done in a one-step process, and you compared the computed output to the target output. The output itself was not fed into the network as part of training. In these sequence problems, we're going to cheat. We're going to provide the output also as part of training, just to control the training process. So this, what we are doing here, doesn't match what we have learned so far in terms of how to train a network. Here's what we will do. We're going to give it, I ate an apple in the beginning, and it's the end of sentence marker. This one is an SOS, right? It's going to generate a probability distribution. If I randomly drew a word from it, it's highly unlikely that the word you're going to draw, at least when the network is not yet trained, it's highly unlikely that the word you're going to draw will be ish. It won't be, right? So what we will do is to say, I'm not going to use the word that I actually drew. I'm actually going to give it the word that I want it to generate, ish. So this is what we call teacher forcing over here, right? You give it you assume that it has actually drawn the output required, and then you feed it the word ish. Then it's going to generate a new distribution. Then once again, instead of drawing a word from it, you're going to assume that it actually generated the word harbor and feed that back in. So does everybody see how we are cheating over here? Right? But we're going to do this. And now you have a sequence of probability distributions. You can compare these probability distributions to the actual words required, and then you can train your model. Clear to everybody? Right. And so the forward pass, input the source and target sequences. Sequentially, you're also inputting the target sequence. This is the cheat. And the output is going to be a probability distribution of this target symbol set at each time. You're going to compute in the backward pass, you're going to compute the divergence between the output distribution and the target word sequence, and back propagate this divergence to all the way to train every portion of the network. Yes?
So, how do we calculate the accuracy? Is it word by word, or is it for the whole sentence?
So this is just, you're just computing a sum of KL divergences. So there's no accuracy per se, right?
Okay.
Right. So anyway, this is for training.
The train.
Pardon me?
The train accuracy.
So train accuracies, for train accuracy, you'd have to perform inference with this model, and then you get your standard Levenstein distance, right? So, but this is for training. Now, we've also, the first sequence should have an SOS Zika. This is just, I have been careless, right? Anyways, now, you don't actually need an SOS for the input sequence because it's implicit, but yeah, in principle, it should be there. Now, as an engineering solution, you may not actually compute the total derivatives over all of these. You could just randomly choose a word from this set and backpropagate just that derivative, which is what the original authors of this work did. And so the overall training algorithm is going to be, you'd have pairs of training instances with the input-output pairs. You'd forward pass, you'd compute the output of the network for an input. And then in the backward pass, you'd select a random time and then compute the derivative and push it backwards. So there's some tricks of the trade. Here, for example, when I'm trying to overload all the information in this final node over here. But typically, by the time you get there, you're going to forget what happened in the initial portion of the sentence. Whereas for generation, knowing what happened in the initial portion of the sentence is very important. And so a standard trick of the trade is they flip the sequence. It starts with EOS and ends with SOS. Again, there should be an SOS over here. So you go backwards. And so by the time, you don't even need an SOS in this case. And then the representation is going to be more heavily biased towards the initial portion of the sentence than the latter portion. And then you can use this to generate text and use the same thing. So if you're reversing the order of the input, you'd have to do this both during training and inference. Guys, by the way, before going away, I'd appreciate it if you could come down here, at least some of you wear these masks and such like, we will take a picture. Okay. So overall training, given several training instances, forward pass, compute the output of the network with the input in reverse order. backward pass, compute the divergence, and propagate derivatives. So this thing works really nicely. Machine translation, my name is Tom. These are examples from the paper. My name is Tom, ich heiße Tom, mein Name ist Tom. Automatic speech recognition, the input would be a speech recording, the output is the sentence. You can use this for dialogues. I have a problem, and then the output is going to be, how may I help you? But you can also use this for image captioning. The input could be an image, and the output could be the caption. So here is the nice thing. We are sort of putting the entire representation of the input sentence on the hidden representation in this red box, right? How good is it? These authors in the paper actually computed it for a translation task, and then computed two-dimensional projections for various sentences and plotted them. And you see this. John admires Mary. John is in love with Mary. John respects Mary. Mary admires John. Mary is in love with John. Mary respects John. Observe how all three are very similar sentences. Their patterns are the same, right? In fact, the arrangements are the same. The positions are different. And the positions that are different because John admires Mary, Mary versus Mary admires John is the same as John is in love with Mary versus minus Mary is in love with John. So the hidden representation actually seems to capture the semantic structure of the input. It's pretty amazing. Same thing over here. I was given a card by her in the garden. In the garden, she gave me a card. She gave me a card in the garden. She was given a card by me in the garden. In the garden, I gave her a card. I gave her a card in the garden. You can see that they're all different sentences, but the arrangements are the same. The relationships are the same. The network actually seems to capture the semantic structure and the data, right? Here are some examples in machine translation. I'll leave them on the slides. You can take a look, but they're actually pretty darn good. This is for a dialogue system. Machine, what is the error that you're running, please? Human, I'm seeing an error related to VPN. The machine, what is the error message that you're getting when connecting to VPN using Network Connect? The human has responded, connection refused, or something like that. May I know the version of the Network Connect that you connect? I'm not sure I know that. Is the Network Connect prompting for any user certificate? This looks very much like a human being speaking, right? This is just a dumb dialogue system, a sequence-to-sequence system. And how would you do this for generating image captions? Instead of having the encoder analyze input text, it's now going to analyze an image, and that representation is going to go into the decoder. And that's the one that was actually, the image analyzer would be some CNN or something, which generates a hidden representation, which just goes into your language generator. And the training is the same as before. You'd have image caption pairs, and you train the network. So, of course, when you're training the network, you wouldn't update the image feature extractor. These examples that we saw early in the class, these were obtained using exactly this network that we just saw. There are examples, there are various variants. Instead of having this guy communicate only with the first hidden state over here, you can have it directly communicate with all of the hidden states at all times. So also for the image captioning and so on. There's an example where they use this for video captioning, where they generate a hidden representation for a video and use that to generate text, and it can caption videos. It's such a simple model, and it works amazingly well. I'll stop here, but all of this has a problem that was mentioned very early in class. That little red box is carrying all the information about the input. You're overloading the poor guy. He's being burdened with the responsibility of the world on his shoulders. That's not the way it should be. So how do we work around that problem? We'll see that in the next class. Thank you. Right.